Hi, I'm Neil Dixon. Welcome to the fourth video in this tutorial on assembly language. Last time we wrote some functions to draw lines, but we didn't look at the nature of function calling. This time we'll get a fairly thorough idea of what's involved with calling functions. In this video, we'll be implementing what's known as flood fill. Before we leap into function calls, I thought I'd take this opportunity to look at what general registers we've got in a bit more detail, now that we've seen some in use. We've only used double-word registers so far, but two in particular we haven't seen: the stack pointer, ESP, and in some cases the base pointer, EBP, are quite important for function calling, as we'll see soon. The rest can be used for just about anything, as we've been doing. The low-order words of these double-word registers can also be accessed directly. For example, writing a value to AX writes the value to the low 16 bits of EAX. The names of these are just the names of the 32-bit registers without the E at the beginning. The E was added to stand for extended when 32-bit registers were first introduced on the 386. Somewhat stranger are the 8-bit registers. Only AX, BX, CX, and DX are split into byte registers, and instead of just being the low byte, both bytes are accessible individually. AL is the low byte of AX, and AH is the high byte of AX. For example, writing a value to AL writes to byte 0 of AX, which is also byte 0 of EAX, and writing to AH writes to byte 1 of AX, which is also byte 1 of EAX. CL has the special purpose that it can be used to shift bits by a variable amount, as mentioned in the last episode. Moving on to the main topic of this video, the question is, how can we call a function? One possible option is to simply jump to the function, and to return, just jump back. The big problem is that then the function always jumps back to the same place, so it can only be called in one place. That defeats the purpose of having a function in the first place. Another possibility is to have a global variable that stores the return address for each function. This was actually used on some computer systems from the 70s and before. However, it doesn't support recursion or multi-threaded code, since then the function could be called more than once before returning, writing over the first return address. The solution that has now been settled on is to save the return address in a chunk of memory known as the stack. The stack is similar to the data structure of the same name, storing chunks of data called frames, one for each function call level. One quirk to note is that the stack grows downward, from high addresses to low addresses. When calling a function, the caller needs to pass parameters to the function being called. These values can be passed by placing them in registers before the function is called, or by placing them in the function stack frame, or some combination thereof. The way that a function expects its parameters to be passed and how it manages local variables is known as its calling convention. The so-called standard calling convention, or __std call in C, accepts all parameters on the stack, and then the function is called. It uses EBP as a pointer into the stack frame, from which parameters can be referenced, so the old value of EBP must be saved on the stack too. The easy way to remember where EBP points in the standard calling convention is that it always points at its previous value on the stack. Finally, we need somewhere to put local variables, now that we're in a new function. These variables are simply placed farther down on the stack, and they can also be referenced relative to EBP. Together, all of these make the new function stack frame. Stack frames vary depending on the calling convention, the number of parameters, and the number of local variables, but overall the format is roughly the same. There are several instructions for dealing with the stack. Push inserts the value specified in the operand into the stack. We can push registers, memory operands, and even constants. Pop effectively removes the value from the stack and puts the value into the specified operand. We can pop to registers and memory. For both of these instructions, ESP is updated so that it points to the last thing pushed onto the stack that hasn't been popped yet. This is referred to as the top of the stack, even though it has the lowest address of anything on the stack, because, as you saw before, the stack grows downward. Note that push and pop can be implemented using move, add, and sub, and in fact aren't used as frequently anymore, because making space for parameters once and moving the values onto the stack for each function call turns out to be a bit faster in most cases. However, push and pop are easier for most people to visualize, so that's what we'll use for now. The pushf and popf instructions give access to the flags register, which, among a few other things, contains the condition flags we saw in the last episode, so these can be useful for saving the value of the flags. Call we saw last time. Literally speaking, it pushes the instruction pointer, then jumps to the function. The instruction pointer, when starting the call instruction, contains the address of the instruction following the call, meaning that the value pushed onto the stack is the return address. Ret, short for return, literally pops that value on the top of the stack into the instruction pointer, so that the next instruction that is executed is the one at the address pushed onto the stack. Specifying a constant as an operand to ret clears the specified number of bytes from the stack after returning, which is useful for clearing parameters from the stack, since they appear above the return address on the stack. If you have 12 bytes of parameters, the constant you'd specify is 12. Note that not clearing the stack properly before returning, or not returning at all, means that the next instruction executed may be unpredictable. The CPU may end up executing arbitrary data as if it is code, and odds are high that the program will crash soon after, but it may just do strange things. This makes stack balancing errors one of the most chaotic, so be careful. Inventor IDE doesn't yet identify stack imbalances, but it will eventually, which should help some. What we're implementing this time is the simple recursive version of floodfill. Floodfill takes an image and fills in a connected region of a single color, starting from a pixel of that region. At each pixel, if the pixel is the background color, floodfill fills it in with the new color, and calls itself recursively on all 4 pixels around, and then returns. If the pixel is some other color, including the color being added, it simply returns, because it has either reached a pixel of the border, or one that has already been filled in. That's really all there is, since we won't be doing bounds checking. You'll need to make sure that the region you're filling doesn't hit the outside of the image, or the program may crash trying to access memory outside of the image. Okay, so moving on to the coding, let's first figure out what it is we're going to be calling. So let's make a function called floodfill, and this function, this fills a region of a particular color with another color. Okay, so the first thing we're going to do is set up our stack frame. So this is done by pushing EBP and moving EBP into it, the value of ESP. And finally, at the end of our function, we're going to clear up the stack by popping EBP and returning. Now, the question is, what is this doing? Well, we're going to have a number of parameters coming into flood fill, and we need something from which to refer to them. So we're going to refer to them relative to EBP, and this sets EBP to the value of ESP, so pointing into the stack. So the question first is, what are our parameters going to be? So let's take a bit of a look at the stack. So at EBP, it always points to its old value. So it points to old EBP. And right above it on the stack, so at +4, it's going to be the return address. Now our first parameter, well, let's say it's the pointer to the bitmap. We're going to need to point to it. So pbitmap. And we'll need to keep track of what pixel index we're at. So let's make the next parameter the current index. Next we need to know what color we'll fill in. So that is at 16. This is the color that we're going to be using to fill in. And we also need a color that we're covering over. So this is the old color of the region. And lastly, because we need to update the index, we will need to know the width to move up and down. So this is the width of the image. Okay, so these are the things that we're going to be keeping track of as far as parameters go. Now, what is it that we need to do in flood fill? Okay, so first of all, let's handle the base case. We want to check to see whether the color of the current index is the one that we're trying to fill over top of. So, I'm going to check that the pixel color is the one we're covering. Okay. So let's load the pointer to the bitmap into EAX, just for simplicity. So that is at EBP +8. So that is the pointer to the bitmap. So we're going to want to find the address of the pixel that we're looking at. So let's load the index into ECX. And the index is at EBP +12. There we go. And we will want to multiply that by 4 because we have 4 bytes per pixel, and you can do that by shifting left 2 bits. It's the same as multiplying by 4. And we want to add these together. So then we get that this calculates EAX is pointed to the bitmap plus 4 times the index, which is going to be the pixel address. Okay, so that gets us the address of the pixel. Now we want to check whether it is the right color or not. So let's move into ECX, the color that we are covering over. See if it's the same. Okay, and we're going to compare the color at the address that we've calculated with the color that we're covering over. And if they're not equal, so if we've reached the boundary, we want to skip over all of the code inside of this function, and let's put line label done right here, so it'll immediately return. So once we've determined that we are going to do the stuff in this function, we want to set the pixel color to its new value. So we can move the color into EDX, let's say, and the color is EBP plus 16, and we still have the address in EAX as we calculated before, and we're going to set the value to this color. So that covers the stuff that is done in a single call. Now we want to recurse. So let's first recurse right. So moving right, we are going to want to add 1 to the index. So a bunch of things don't change, so we can just push them again onto the stack. So for example, the width doesn't change, and that is the first thing that we're pushing onto the stack. So that's EBP plus 24. Then the old color doesn't change and the current color doesn't change, so we can just push those on again. Now the index is changing, so let's move the index into ECX. EBP equals 12, so that is the current index, and we're going to add 1 to it. Okay, so that's now the pixel that is 1 to the right from the current pixel, and we're going to push that onto the stack. Lastly, we're going to push the address of the bitmap, which also hasn't changed, and we call floodfill from within floodfill. So this is the recursion here. Now, recursing left, up, and down is very similar, so let's just copy and paste for now. So this will be left. So recursing left, we're instead going to subtract 1. Recursing up, we're going to subtract the width. Now the width is in EBP plus 24, so we can just do that. So we're now subtracting the width from the index and pushing that new index. And recursing down, we're going to add the width to the index. So let's save that. Now one thing that I mentioned earlier is that you can add a constant after a ret that clears up parameters from the stack. And in this case, because we aren't clearing the parameters from the stack after calling floodfill here, we'll need to do it in this ret instruction. So how many bytes of parameters do we have? Well, we have 4, 8, 12, 16, 20. So we have 20 bytes of parameters. So saying ret 20 will add 20 to ESP after returning. That will clear the parameters off of the stack, so that we don't have to add to ESP manually. So the only thing left that we haven't done is calling floodfill initially. So with the image I have prepared, I know that at the coordinates 105, 89, there is a white pixel that will be colored in, and so let's try to fill from there. So The first parameter that we have to push, though, is the width. So let's push the width, and the width here is in EAX. Now next we have to push the old color. Now I know that the pixel is white, but let's say we didn't know that, and find what color is at that pixel to start with. So the coordinates we're starting from are 105, 89. So let's move into EDX 89. So this is our height, or our y coordinate. And we're going to want to calculate width times 89 plus 105. So that will give us our pixel index. So let's multiply the width in EAX times EDX. Oops. Yeah. Mul only takes one operand and it multiplies it by EAX. And next we'll add to EAX 105. And there we go, that's calculated our pixel index. So the color that we've got is going to be at EAX times 4, because we have 4 bytes per pixel, plus ECX. ECX is the address of the bitmap, and this is the address within that of the pixel. So next we push the new color. So push, and let's say the color is 4080 FFH. So that's red, green, and blue components. So next we want to push the index, and we've just calculated the index. It's in EAX, so let's push EAX. And finally we want to push the address of the bitmap, and that is here in ECX. So that was fairly simple. And finally we just call flood fill. Okay, so let's save that, and hopefully this works. And there we go. We now have our image filled in that component. So one thing I said a few times is that a lot of these parameters don't change. So one thing that you can do is, instead of passing them on the stack, you can pass them in registers. And this works best with parameters that don't change when you're recursing. So let's, instead of passing the width on the stack, let's pass it in EBX. And there we go. So that means that when we initially pass it, instead of pushing it, we want to move it into EBX. Okay. So now we don't want to push it all of these times. It will just stay in the register EBX. Okay. And suppose the old color, we have it in, let's say, EDX. Okay. So now, instead of pushing it on the stack, we'll be moving it into EDX and not pushing it. Now one thing to note is that we're using EDX here, so we should probably choose a different register there to use, so that we don't write over the value of EDX as we're using it. Okay. so the color also doesn't change. So let's say we pass that in ESI. So the color here, move into ESI, the color, and then we don't push it. Okay. And lastly, the pointer to the bitmap doesn't change. So let's pass this in EDI. Okay. So, the last thing we need to change is that we no longer have 20 bytes of parameters on the stack. We only have 4 bytes of parameters on the stack. So we clear that up with ret4. Now, one thing to note is that it doesn't take a very large image to get flood fill to overflow the stack. We've got a fairly limited stack space, and if you use too much of it, the system will crash. So it's important to try to limit the use of the stack with highly recursive functions like flood fill. So let's try this. It should give us the same result. Nope. It's crashed. Ah yes, silly me. I forgot to change these. We're still pretending that these things were on the stack, when in fact they're no longer on the stack. So now the index is at EBP plus 8, and these are all in registers. So this is the address of the bitmap, so it's in EDI now. This is the index, which is at EBP plus 8. This was the old color. It's now in EDX. This is the new color, and it is in ESI. And this is the index at EBP plus 8. This was the width, which is in EBX now. EBX. There we are. Let's try this again. Nope. Did I miss one? Let's see. Oh, I did miss one. Okay. Last time's the charm. And there we go. Oh, let's delete this to make sure. Excellent. It worked. In the next video, we'll be learning about simple data structures and starting to tackle a cool challenge that will span several videos. Thanks for watching.